Hi, welcome to Yonder Dynamics. Last year our rover Procyon remained far from perfect, but it was a great stepping stone to better things. This year, we have fully redesigned our rover from the ground up. With the competition tasks in mind, we are excited to show you what our new rover can do. This year, we are designing a robust drilling mechanism that will efficiently extract and cache the soil. First, a 12-volt mini-track linear actuator will apply maximum pressure for our long, narrow drill auger. The sample carousel will cycle through 6 chambers, one for each sampling site. It will also house all of the components necessary to carry out our soil analysis. With the elimination of the lab portion in this year's competition, we have poured our efforts into developing an impressive onboard analysis suite. To look for extant life, we are employing a microbiological assay that analyzes bacterial growth in a sample. In the carousel, water, nutrient auger, and our sample will mix together. In a controlled environment, our Arduino-controlled turbidimeters will monitor the total suspended particles in the mixture over a given time interval. We will then compare the data to models of bacterial growth under similar conditions, which we will develop with the aid of Dr. Brian Bish. For extinct life, based on the work of Dartnell et al., we'll use Raman spectroscopy to detect the presence of cellular carotenoids that are present in some radio-resistant extremophiles. That's all for science. Now over to Isabella for motions.
During the design process, the motions team made sure to integrate our systems by collaborating, communicating closely, and hitting our deadlines. We used SolidWorks for CAD and Google Drive file stream to manage our data across a relatively large team of about 40 people. Compared to last year, UCSD and Qualcomm have provided us with substantially more resources for machining our parts, so all of our components will be machined to substantially higher specifications than before. We're depending on the drivetrain and chassis reliability, off-road ability, and precise movement for every task in the competition. The suspension worked well last year, so we used that design as a foundation to improve upon. We completely redesigned the chassis out of carbon fiber and aluminum tubing. The back two wheels shock absorption system was also redesigned with improved range of motion, and the wheel system uses flexible material in innovative ways. We have tested a few iterations of the wheel and suspension prototypes so far, further improving our design. We're using the arm for the extreme retrieval and delivery and the equipment servicing tasks. We have completely redesigned the arm out of carbon fiber tubes and aluminum end blocks, making its main axes cable-driven from the base, with the wrist being driven by a differential gearbox. We hope to be able to easily lift over 5 kilograms and have a large degree of precision. We plan to have the rover's initial iteration functional approximately 3 months before the event. We will then focus on testing the rover in an environment with similar conditions to the URC. We will also run the arm through a series of tests resembling those it will face in the URC.
The software team has designed a diverse software stack to address the unique challenges put forth by the University Rover Challenge. Our lowest level systems run on a DE0 Nano Development Board, which connects our core systems via Ethernet to an Altera Cyclone 5 FPGA for fast, precise motor control and encoder handling.
To run our autonomous systems, we use the NVIDIA Xavier, which is equipped with a GPU powerful enough to run our autonomous algorithms. Following our on-site testing at URC 2018, we have built upon our existing autonomous systems with general improvements to our controls and path creation. We have also designed a search system that utilizes incomplete information to help speed up our search, and we have upgraded our tennis ball detection to make it light and variant. However, we don't just want computers and computer-like people to drive the rover. Instead, we want to make it accessible. Our control panel is a web app that allows nearly any device to be used as ground control.
Boxes for each subsystem. These boxes will contain our own in-house designed PCBs, protecting them from dust and dirt during transport and competition. This will allow for easier connectivity between subsystems of the rover, a reduction of messy wire nests, and a streamlined debugging process. After constructing a power budget based primarily on motor choices, we've decided to use 5 5200 mAh 11.1 volt batteries, 4 for the drivetrain, arm, and onboard sensors, and 1 dedicated to the brains of our rover.
We have high hopes of what our rover is capable of for the URC. Thanks for watching, and we hope to see you in Utah.